This is an example about the power consumption in an agitated vessel. So example number 1 here is saying that you have a flat blade turbine with 6 blades. So we have already mentioned what the type of turbine that we are using. A 6 blade turbine is installed centrally in a vertical tank. The tank is 1.83 in diameter. So you must make sure that your tank is, this is your value of dt. The turbine is 0.61 meter. This is your dA, right? And its position 0.61 meter from the bottom of the tank, right? So this is the value of E. The turbine blade has the prevalence blade are 127 mm wide. So this is the value of W. The tank is filled to a depth of 1.83. So this is the value of H. With a solution of 50% caustic soda at 65.6 degrees Celsius, which has a viscosity of 12 cp, right? Make sure that you know cp is centipoise, so this is the value of your mu, and a density of 1498 kg per meter cube. This is the value of rho. The turbine is operated at 90 rpm. This is the value of N. So what power will be required to operate the mixer if you have the tank is baffled and the tank is unbaffled? So you have two conditions. First one is what is the power requirement if the tank is baffled? The second one is that what is the power requirement if the tank is unbaffled? So it is quite straightforward. So this is an example of solution, right? So first of all, as I mentioned just now, always change the value of N from RPM to RPS. So 90, so just divide by 60. So you will get 1.5 RPS. And we just mentioned that dA is 0.61, right? Your viscosity is 12 cp. Now cp has the same unit as 12 times 10 to the power of 3 kg meter per second. So if you look at the equation for Reynolds number, you know the value of your dA 0.61. So I'll just do the unit constellation here, right? So 0.61 meter squared times the value of N, which is per second, right? 1/second. The unit for density is kg per meter cube, right? And then the unit for viscosity is kg meter per second, right? So if I look at here, meter squared times meter is meter cube. So I can cancel out my meter cube. Kg can cancel out with kg. Second will cancel out with second. So I will get a dimensionless number, and if I put all the value in the calculator, I'll get a value around this value 69600. Now based on this value, now if you look at here, so this is for 6 blade turbine. So I'm going to be using this chart, this graph here. So first of all, I need to know whether I want to use curve A, curve B, curve C, curve D. So here from figure 9.12, I'm using curve A. So how do I decide whether I want to use curve A, B, C, or D? I can find the value of S1, S2, S3, S4, S5, and S6. So usually you can just find, usually the values you can find are S2, maybe, and S. Because if you see here, all the values are same for S1 until S3. So based on the value of S4 and S5 and maybe S6, I know that the curve that I'm using is curve A, right? So that's why I state here I'm using curve A. And then I mentioned just now, this is 1000, this is 10,000, and this is 100,000. So 10,000, 20,000, 30,000, 40,000, 50,000, 60,000, 70,000. So around here, so 69,000, right? So the point is somewhere around here. So from here, I can find the value of my power number and it is around 5.8. So I don't have a ruler, so you can actually try to use a ruler to actually find the correct value of the value here. So this is just an estimate from my side. I get around 5.8. So now that I have gotten the value of power number, and since my RE is, even though it's greater than 300, right? It's greater than 300, but my tank is baffled. So there is no need for me to find the Froude number, because for a baffled tank, the Froude number effect is neglected. So I can still straight away use the equation for P. I know the value of NP, which is 5.8. I know the value of N, which is 1.5. dA is 0.61. Rho is 1498. And since everything is in SI unit, so GC is equal to 1. So I can just ignore the GC here. And I will get the answer 2476.6 meter Newton per second. Or you can always change this and you can get a value of 2476.6 watt. So this is the final answer for A, for a baffled tank. Now let us look at for B. For B is saying that it is unbaffled. So unbaffled, and then from our previous question, we know that our value of RE is actually 69600. So it is definitely above 300. So for unbaffled and above 300, the Froude number will always come into effect. And then we know that we are going to be using curve D here, right? Because curve D is the one for our unbaffled tank. A, B, and C is for baffled, D is for unbaffled. So from this curve, I can get an estimate value of my power number is around 1.07. Now before I plug in this value into my power equation, I need to find the value of NP corrected. How do I do that? First of all, I need to find the value of Froude number. So I know the value of N, I know the value of D, and I know the value of G, which is our gravitational acceleration. I get a value of Froude number is equal to 0.14. Next, I find the value of M. So for a 6-blade turbine, the value of A is 1, the value of B is 40. So I substitute into this equation, and I know the value of Reynolds number is 69,600. So I get a value of negative 0.096. So the equation for the corrected value of NP is equal to NP 1.07 times the value of NF 0.14 to the power of M, which is 0.069. So I'll get a value of NP is equal to 1.27. So you can see there's a difference between the value of the original NP and the corrected NP. Once I've gotten this value, I substitute again into this equation. 1.29 times the value of rotational speed, 1.5, times the dA, 0.61, times the value of density, 1498, I'll get a value of 550 watt. So this is the final answer for question number